Good morning, happy Monday. We're going to continue our discussion of the shapes and sizes of polymer molecules in solution and in the solid state. So this is not new material, this is just from last time, and we talked about the fact that while we draw polymers as extended chains when we draw the structure, of course this is a very low entropy state, right? It's only one possible state of many, like a gazillion possible conformations of the polymer in solution. So in order to maximize, or because the states available to the polymer have to be maximized, of course, being all in a straight line is quite improbable, right? So normally what happens is that the polymer balls up into a blob like this, and the blob has characteristic dimensions, which the radius of this blob, which is say from here to maybe somewhere around here, is the radius of gyration, RG, which is essentially the average distance, the root mean squared distance of one of the monomer residues in the polymer chain to the polymer chain's center of mass. Now, if you do the algebra out, we're not going to do it, but the radius of gyration equals the length of the monomer, which is, let's say, on the order of 1 nanometer, times the square root of the degree of polymerization, I. Note, this is not the imaginary number. This is the degree of polymerization, and let's say that it has 10,000 monomer residues in it. Then divided by the square root of 6, we get 40 nanometers. So a polymer blob in solution is a nanoparticle. Now, a lot of this space, though, is not taken up by the polymer, by the actual electron density of the atoms that make the polymer up. So let's compare the actual volume of the polymer to the gyration volume. So if we can approximate one segment as a cylinder that has length L, so this is one segment, and we approximate it as a cylinder with length L and diameter L and radius L over 2, so it's kind of like a square cylinder. That's not a thing, but its diameter is the same as its length, just to make the math easy. And then we have the actual volume is equal to pi r squared, and r is L over 2 squared times L times the number of these segments that you have, which is roughly I to the L cubed. And the gyration volume, the gyration volume is different from the actual volume because it's the amount of, it's sort of like the three-dimensional footprint of this gyrating blob of monomer residues. So the gyration volume is 4/3 pi radius of gyration cubed. So just 4/3 pi r cubed, assuming that this is more or less approximatable as a sphere, as we like to do as engineers, is approximate things as spheres. And this gives us 0.3 roughly L cubed times I to the 3/2 power. And what is a consequence? If I equals, say, 1,000, then only 10% of the gyration volume is actually occupied. So if I equals 10 to the 3, only 10% of the gyration volume is actually occupied What is the rest? Solvent. Solvent could be water, could be toluene, could be anything. And the extent to which the solvent interacts with the molecules of the polymer, or the residues of the polymer, affects the size of the polymer blob. Now, in the freely jointed chain model, we don't take into account the solvent. This is just a purely statistical construction. But if we have a bad solvent, a solvent that does not interact very well with the monomer residues, then do we think the polymer blob is going to shrink or expand?
Unless it favors itself.
It favors itself, so it's going to shrink. Now, if we have a polymer, say we have polystyrene, which is a polyolefin, this zigzag CH2 chain with some pendant benzene rings on it, and we put it in benzene, is that a good solvent for that polymer? Yeah, because it's sort of like polystyrene, so it might tend to relax a little bit and expand. So this argument is valid in an ideal solvent and no intersegment interactions. And an ideal solvent is neither bad nor good. So in an ideal solvent, it behaves just as the statistics say that it would behave. Valid in an ideal solvent with no intersegmental interactions. But in a bad solvent, and let's say this is chemically dissimilar, interpreted broadly, just doesn't particularly like the monomer residues compared to how much it likes itself. And the consequence of a bad solvent is that the coil shrinks. Coil, blob. I used to think, I think the word coil used in polymer science is a little bit of a misnomer because we think of a coiled snake, but a coil in polymer science means like the coil of speaker wires behind your TV or other place you might have a big tangled mess of coiled wires. Yep.
Is it shrinking the radius of gyration when you have bad solvent?
Yes. And in fact, in that case, and I'll get to it, the radius of gyration has a different name in the case where you have a non-ideal solvent. So a good solvent the coil expands, and in both of these cases, the actual radius is called the Flory radius, after famous polymer scientist Paul Flory. Or was it radius? Is RF. So far, so good? Okay, this gives us an idea of the sizes of polymers in solution, but we don't usually engineer polymers for materials applications for their solution properties. We care about what happens to them after we solidify the film. So what is the polymer microstructure and nanostructure. It's called microstructure, but because you look at it under a microscope, but really it's nanostructure because we're nano engineers and we want to call everything nano because it is nano. Okay, so what is the nanostructure, formerly known as microstructure, of a polymer solution upon either crystallization, so you either take the melt and you cool it down. There are two ways of making a solid polymer. Maybe three ways. You take the polymer in solution and you cast a film, or you pour it into a mold or something, and then you allow the solvent to evaporate, and then the film solidifies. You could also take a polymer and melt it. It'd be a thermoplastic, and then it forms in a new shape. Or it could be a thermoset polymer, which is a polymer that undergoes a chemical reaction to become a solid material from a liquid precursor. So micro nanostructure of solid polymers. So the crystallites, and this is in a typical solidification from, could be a melt or could also be from solution. But this is sort of the typical case. There are a lot of atypical cases, but this is the sort of a typical case. And what happens is that we have, in any polymer solution, any polymer film, we always have amorphous material. We always have amorphous regions like randomly oriented spaghetti. But in some places, we could have crystalline regions where the spaghetti sticks together. Like if you make the spaghetti and you don't stir it after the first minute, then it sticks together in certain places, and you're never going to get it apart again. Other types of high aspect ratio noodles also exhibit this behavior. So anyway, you stir it apart, you stir it, and then it's all amorphous. But sometimes you get clumps where the strands are all together. Those strands occur in solid polymers too, and they're called crystallites. I think Crystal Light was a beverage in the 90s. They might still have it. But anyway, it's called a crystallite as opposed to Crystal Light. So crystallites nucleate and grow radially outward from a center nucleus. So we have three regimes of growth, and here is a cross-section of a solid polymer as we solidify the polymer. Cross-section this is nucleation. And let's say we get a nucleus here, here, and here. And these nuclei could be formed from density fluctuations. Which is, in any system that has some finite amount of thermal energy, you're going to have the chains moving around, and in some cases they'll lock into place at a relatively high density at the right in the right position, and they'll form a crystallite, a nuclei of a crystallite, and it will grow outward from there. The other way that you can nucleate a solid polymer is an impurity. which can trigger the solidification around it. Has anybody ever seen that experiment where you take a super smooth glass jar or flask, you fill it with ultra pure water, and you cool it below 0 degrees C, and then it's still liquid. It's still liquid, and then when you take it out of the cooler and you give it a shake, and it turns into ice immediately. The reason we need super cool liquid or super pure water is to avoid impurities, and the reason we need density, or the reason we shake it, is to induce a density fluctuation in order to get it to crystallize. One time in grad school, I had never actually seen this lab demo done, and one of my postdoc colleagues, who's like a scientist who already had his PhD and went back to school like you do if you want to be a professor. But anyway, that's what a postdoc is. So the postdoc came in to the lab and carted in this cooler, and then he took one flask out and another flask out, and he did this experiment. And I thought, oh well, that's really cool, and it's especially cool that they didn't solidify by accident while they were still in the cooler after he wheeled it in there. And then he just kept taking out flask after flask just to demonstrate, and it was incredible. Not like the amazingness of the process was stupefying, but then the fact that he fit like 10 flasks in not a very big space, it took over the sense of wonder of the physical thing. And then he just kept taking out like, yeah, I get it, but holy crap, how many flasks you got in there? It was like fitting clowns into a VW Beetle. Or bug. Anyway. Okay, nucleation, then growth. I never focus group tested that anecdote before. I hope it was okay. Growth, what happens in growth? The spherulites get bigger. So crystallites nucleate and grow, and these are called spherulites. Why spherulites? Because of their rectangular shape. Now they have a spherical shape. This is the cross section, so they're circles. If you look at the spherulite under cross-polarized light, it has a very distinctive pattern. So under cross-polarization in the microscope, you get a pattern that looks like this, which is the sigil of the island of Malta, and it is called a Maltese cross. Malta being across the narrow sea. And what do you get? Why does it form this? Well, it forms this because of its the way that it scatters light. So cross polarization means that you illuminate from the bottom of the sample, but you have a cross polarizer in the bottom, and then a polarizer at the top that's oriented perpendicular to the first polarizer, and the sample's in between. Now, ordinarily, when light comes through with no sample in between, just like in an LCD display, all the light would be blocked and you'd see nothing. But because these oriented polymer fibers within the spherulite rotate light, in certain regions you get this cross pattern developed, and that's indicative of crystallization, and we'll look into what exactly this microstructure is in just a minute. Then you have impingement of these blobs, and let's say that they have been growing outward like this, and they run into each other and they can't go anymore. It's like bubbles merging into each other. And then eventually the whole thing is these spherulites. Now, while the spherulite is a crystalline structure, I'm going to show you that a cross-section of a spherulite is more like a snowflake. And in between the branches of the snowflake, you have amorphous material. So it's not entirely crystalline, even though these things form because of a tendency to form ordered crystalline structures. So what do these look like, and why do they give us this cross pattern? So here's the I had all the time in the world to hit the bullseye and I blew it. Okay, so we get these snowflake-like patterns where we have these highly branched structures that grow outward from a central nucleus, and let's draw some branches on the branches. Okay, this is the cross-section of our spherulite. Now let's take a closer look. These are not polymer chains, but they are made of polymer chains, and probably not in the way you expect them to be oriented within the structure. So let's take, what do I mean by these two branches here? So these two ends are these two ends. Is that okay? And how do the polymer chains orient within these crystallites? The polymer chains form these hairpin turn structures. That fall back on themselves they form these 180-degree turns. In some cases, this is a particularly well-ordered structure. Sometimes you'll have loose ends that exit the switchboard and come in somewhere else, but they're still within the crystallite. The axis of the polymer chains are side by side. And what does this look like? What is this? This is a polymer chain that, in the case of polyethylene, is just that. Is that okay? In between these strands is amorphous stuff. So all in here is amorphous. And the branches are the crystallites. And you have amorphous stuff in between. Note that the molecular chains are perpendicular to the fiber axis, to this crystallite axis. Polymer chains perpendicular to the axis of the crystallite. Okay, so this is how a very large fraction, so let's say most polymers actually exist in the solid state. You take a microscope and you would have some kind of a crystallite structure that has this spherical, this spherulitic microstructure. Now, crystallites can form, and there are a lot of unconventional polymer microstructures as well, which are quite important technologically, but this is typical. There are a couple different ways that these polymer chains can orient themselves within crystallites. And the one that I tried to draw there is called the adjacent reentry model. The adjacent reentry model, which exists under when the molecules have a lot of time, so thermodynamic control. When the molecules have a lot of time, they'll, instead of re-entering over here, they'll just re-enter right where they exited. Now, what's the alternative? The alternative is the switchboard model. This is the switchboard model. Switchboard model tends to be the form that is found in spherulites. So this is perhaps a little too ideal. Tends to form in spherulites. The adjacent reentry model tends to form when crystallites are formed from solution. Tends to form in solution. Yeah, so you see the difference here? Switchboard model, why would it be called switchboard model? Well, when this was first hypothesized, when you wanted to make a phone call, you called the operator, and the operator took a peg out of a switchboard. This is even before I was born. You take a peg out of the switchboard and you plug it in to where you want to connect the call to. Take this one, you plug it into where you want to connect the call to, and so on. And that's how in ancient times, that's how calls were made. Yes?
You said the spherulites tend to form in solution in a situation like this. So is one like a very carefully cooled solution?
This is more common from the melt. Sometimes you can get the structure from solution, but it's more common from the, well, you can get spherulites both ways. Let's say that the switchboard model is, there's a gradation, right, between purely adjacent reentry and purely switchboard. Nature likes to tend toward a more disordered structure, and you'll always have some loose ends, but these are the extrema of the continuum, where this is believed to be more common. Okay, there are non-spherulitic structures as well. let me clarify. The spherulites that are grown from, there are other types of crystallites that are not spherulitic that tend to form the adjacent reentry structure. The spherulitic structure is almost always like this, whether or not it was grown from the melt or from solution. Yeah. Okay, so non-spherulitic structures are also possible, but these generally form from solution as opposed to from the melt. So you can have single crystals, single high aspect ratio linear crystals. Generally, they have the adjacent reentry model. You can have single crystals that have branches, which are called dendrites. Now this is when the monomers add to a growing chain end so fast they don't have time to grow into a spherulite. So as soon as one end becomes activated, it just shoots out. As soon as one end becomes activated, it's almost like uncontrolled polymerization. This is called a dendrite. And then another non-spherulitic morphology, which has a really cool name. It's called a shish kebab. And this is a type of structure that forms under shear or mixing. This is a shish kebab, and it results from solidification from a solution under shear, like rapid spinning or fiber drawing. So it results from shear. That is, that you might get from rapid stirring. Or fiber drawing. Yes, sir.
A good example of this would be like last time listed in OCAM where we synthesize nylon and then pull it out.
The question is, do you get a shish kebab morphology in the biphasic nylon experiment, which is where you take adipoyl chloride and a diamine, and you mix them together at an organic phase and a water phase, and as you pull out the material that forms at the interface, you get long structures, and that's how like fishing line is made. The question is, I bought myself enough time. The answer is, I don't quite know. You certainly have alignment, like the structures between the crystallites, and in some cases you might have structures like this, but it's more the tensile strength of nylon is a result of the drawing process, but I don't know if you get the kebabs. It might just all be sword, might all be skewer. Certainly have some other structures in there, but primarily it's just because of long drawn out structures. Okay, these are not the only microstructures or nanostructures available to polymers. In fact, we can design the molecular structure in such a way that it gives us much more interesting and useful, and in some senses, deterministic structures. And one of the best tools of doing this is called a block copolymer. Sometimes called a BCP. And what was found in polymer science in the beginning days of plastics is that if you wanted some property from polymer A and some property from polymer B, you would just mix them together and you would hope that you would get the best of both worlds. Now, that doesn't happen because polymers, for reasons that we'll go into if you take my class Nano 134, polymers don't like to mix with each other. Most molecules don't like to mix with each other unless there are specific interactions like positive and negative charges or perhaps shape that allows them to mix to each other. With polymers, this is especially bad because the reduced amount of statistical microstates available that you have once you start linking molecules together to form polymers, they tend to phase separate because one polymer is going to like itself more than the other one likes it or likes itself. And that's what drives phase separation in media, and especially strongly in polymers. So with a highly phase separated blend, you don't ever get the best of both worlds. You don't usually get the best of both worlds. You usually get the worst of both worlds. So say you want to have some optical property like transparency, but you also want stretchability or something, and you mix two materials together, you might end up with something that's opaque and brittle. So block copolymer is a way to get around the thermodynamics of polymer phase separation. And what you're doing is you're permitting, what the strategy is to take A and B and to link them covalently so they can't phase separate. Now, in fact, they do phase separate, but they can only phase separate on the order of nanometers as opposed to on the order of millimeters, which is can be quite powerful. So we usually draw this, or we indicate this as A with N units and B with M units, and this is a block copolymer. Or you could have A sub N, B sub M, and A sub, say, L. L could be equal to N, maybe not, doesn't matter. Or you could have A sub N, B sub M, and C sub L. These would be examples of tri-block copolymers. And what you would do, so a real material, so a typical say polystyrene block lowercase polymethyl methacrylate. Would be written PS dash lowercase b dash PMMA. And there are only really a few block copolymers that are super common in nanoengineering, and then there are a lot of many times that number of specialty materials that are used for specific applications. So polystyrene block PMMA is quite common. Chemically, that looks like this. Where this is the polystyrene block, and this is the polymethyl methacrylate block. So these ordinarily do not want to mix, but they're tied together covalently. They can't escape from each other. So instead of forming two phases like salad dressing, they form these very characteristic microstructures. Again, they're actually characterized by nanoscale domains, but because it was already called micro from the early days of polymer science, those are the names we have. So these phase separate into nanoscale patterns. And this is a quintessential example of bottom-up nanofabrication. So if we start with increasing, so we've got, let's say we've got A block B in terms of mostly B at the beginning and mostly A at the end. So let's say this is 10 repeat units and this is like 1,000,000 repeat units, or some ratio all the way to one side. Okay, that's too big a difference. Let's say 1,000 and 10,000. Okay, so if you got mostly B at the beginning, you get a structure that is called the cubic structure, where in these drawings the filled in parts are A and the contiguous phase is B. This is cubic. And these domains could be somewhere on the order of, let's say, 5 to 200 nanometers. Those are characteristic sizes of all the structures that you'll find in block copolymers. As you increase the amount of A, these blobs become bigger and bigger and bigger until there's a thermodynamically more favorable state for these to be in, where they stretch out and become cylinders. Okay, that's a horrible mess, but you kind of see it. This is called the hexagonal that means we have 5 minutes. Hexagonal phase. And these are cylindrical microdomains. Don't let the name fool you, they're really nanodomains. Then we have my favorite structure, which is impossible to draw, but I'm going to just draw some BS and ask you to look it up. Is called the gyroidal structure, which looks like a contortionist. We are not even going to try. This is like this three-dimensional thing. It's actually a repeating structure in the unit cell. It's called the gyroid. Yep.
Were these on your PowerPoint last week? These are pretty familiar.
Yes, these are on the PowerPoint last week. So you can look up what the gyroid actually looks like if you have a computer to draw it for you, or a skilled artist, which I am not. Then, if you have 50-50, we're not at mostly A yet. Mostly A is over here. When you're about 50-50, you have a structure that looks like stacked pizza boxes. This is the lamellar structure. Now this is the tipping point. We start adding more A, we get all these structures but in reverse. So we get the inverse gyroid, where the filled and the empty parts are now reversed. Inverse hexagonal. Inverse cubic. Now, could I have started with mostly A and added B? I could have done that. In that case, I would have written them all backwards. So these processes are used, why are they bottom up? Because we start with a chemical structure and we anneal the film or we treat it in a certain way and it grows into these structures automatically, just based on the molecular design and the thermodynamics. It forms a structure automatically. We didn't have to do any lithography. We didn't have to etch anything. And these structures are useful for a wide variety of technological applications. So thank you very much for your attention. I will see you on Wednesday.